Greetings and welcome back. Today we're going to be looking at carbon-13 NMR, which is very similar to proton NMR in that we put our samples into a magnet, we get a chemical shift and all of that good stuff that tells us the number of different environments. But in this case, what we're looking at instead of H1 is that we're looking at carbon-13. The largest differences to note. First off, of course, the nucleus of carbon-13 is exactly 13 times heavier than that of hydrogen-1. Therefore, the ppm scale is going to be different because they respond in a different way to electromagnetic radiation and magnets. In addition to that, hydrogen-1 is about 99% of naturally abundant protons. Most of them weigh 1, whereas carbon-13 represents about 1% of carbon samples. In this case, most is carbon-12. Remember that only nuclei with an odd mass have a spin, therefore most of carbon is going to be carbon-12 and therefore invisible in NMR. Remember that there are 4 different things that you can tell by proton NMR, the first being the number of environments, and that holds true in carbon NMR as well. You will see peaks for all of our environments of carbon, and these usually range on a scale of about 0 to, in this case, about 210 ppm. So the scale is much larger for carbons, for carbon-13. What we see is that, first off, we'll have the same number of peaks that we would carbons. So, for instance, in this case, you would have 4 carbon environments, whatever those values are. The second thing that we can tell from proton NMR is the chemical environment, that is to say the shielding environment around that nucleus. Same thing holds true here as well, and they generally follow roughly the same order. Your book tells you that these are about 15 times higher, and that's a good approximation. But in this case, sp3 carbons are going to be from about 0 to about 35 ppm. So they're the furthest to the right because they're the most shielded. And this is similar to how the sp3CHs are the furthest to the right because they're the most shielded hydrogens in hydrogen NMR. Alright, sp3 carbons that are attached to halogens are next. Those guys show up roughly from 30 to 60 ppm. So in a way like we did with proton NMR, this is about 30 higher. So it's about 30 ppm higher for a carbon attached to a halogen than it would be a carbon all just attached to hydrogens. An sp3 carbon attached to oxygen is going to be about 60 to 90 ppm, which is approximately 60 higher than normal. You may remember that carbons in a triple bond are next on the scale. So an sp carbon, which is a carbon in a triple bond, these guys appear somewhere in the range of about 75 to 100 ppm. We don't worry about substituents in this case, so I'm not going to worry about a plus 60 for having multiples of them or anything like that. Alright, sp2 carbons that are involved in carbon-carbon double bonds are going to be somewhere in the range of about 100 to 150 ppm. You may remember that sp2CHs were somewhere in the range of about 5 to 6. These are about 100 to 150. And that's the same whether they are in just a normal carbon-carbon double bond or if they're in one of the double bonds that's part of a benzene ring. Alright, lastly, sp2 C double bond O's, those are having their electrons withdrawn by the greatest amount, therefore they're going to be furthest to the left. They're the least shielded of all carbons in a carbon NMR, and these guys are about 160 to about 210 ppm. So the environments, there's less to worry about with carbon NMRs than there are with hydrogen NMRs, because hydrogens could be close to a lot of things, but in this case it's really what functional group is the carbon a part of. You may recall that there is a third and a fourth thing that we can tell from hydrogen NMR. The third thing is the area under the curve, which tells you the number of protons in that environment. Unfortunately, that doesn't work very well for carbon NMR. Therefore, there's really no integrating to be done for these, and we don't ever have to worry about the number of carbons in that specific environment. Lastly is splitting, and remember that has to do with hydrogen neighbors. Well, carbon neighbors would be incredibly rare for a carbon-13 to be next to a carbon-13. The chances of a carbon-13 are 1%. The chances of two carbon-13s being next to each other is 0.01%. So really that never happens, and so we don't actually have any splitting to worry about. So really the only things we worry about in carbon NMR are the number of environments and roughly where they are by chemical shift. So it's much less complicated. There's much less information in a carbon NMR than there is in a proton NMR. Furthermore, because carbon-13 is about 1% of all carbons, if you have a normal sample that you're putting into an NMR of carbons, trying to look at those carbons, it's going to take a lot more time because you're not going to be able to see them as well because there's just not as many of them in your sample. So whereas a proton NMR might take you a minute to really run the sample, a carbon NMR is going to take hours. We're going to look at a couple samples here, or a couple molecules. We'll start off with this one. We'll put two chlorines attached to a carbon at one end. We'll put a carbon in the middle with two chlorines attached to it. And we'll put a CH3 at the end. Alright, so we would expect that the CH2 on the left, which is only next to one chlorine, will be somewhere in that 30 to 60 region. The CH3 on the right, which is just really all by itself and not attached to anything else, that would be in that 0 to 35 ppm region. And for that carbon right there in the middle, notice that that's attached to two halogens. Since each halogen pulls it up about 30, we would say that instead of being roughly 0 to 30, it's going to be somewhere in that 60 to 90 region. And we can pull up those NMRs and look at them, but notice real quick where the protons would be. So in this case, these hydrogens here, they are attached to one chlorine, so we would say 3 to 4, and maybe a little bit higher because there's two chlorines next door. So this chlorine is directly attached and has the greatest effect, but those two chlorines over there will have a little bit of effect. So we'll say maybe slightly higher than 3 to 4 ppm. Alright, likewise, these hydrogens over here, they're a CH3, and they're not attached. That carbon's not attached to any halogens, but these Cls over here will have a small effect. They might pull it up by maybe half each. So I would expect that guy to show up, and maybe instead of 1 to 1.5, maybe 2 to 2.5 ppm. All right, and so notice that this is going to have 3 carbon environments because we have 3 carbons. 1, 2, 3. It's only going to have 2 hydrogen environments because we only have 2 hydrogens. All right, so let's pull up these 2 spectra and see how we did. All right, so there's those spectra. You can see the hydrogen NMR is down here. We've got a peak around 2 ppm, which is what we would expect, and we have one at pretty much 4 ppm. We said it's a little higher than 3 to 4, so it's at the high side of that. It's actually at 4. And those are our 2 peaks. Of course, TMS is our reference at 0. All right, likewise, our 3 carbons, we had one that's right around 30, which would be this one right here. That's the lowest or furthest to the right. We had one that was in kind of the mid-40s or mid-50s, and that would be this one right here in that 30 to 60 region. The carbon that has both chlorines attached would be the highest of all, and that we see showing up somewhere in the high 80s to around 90, and that's right where we expected it to be, in that 60 to 90 region. So hydrogen NMR, in this case, it's not labeled on there, but of course we could have that integral trace to tell us the area under the curve. This particular molecule doesn't have any splitting because there's no CHs next to CHs, but normally we can see quartets and triplets and things like that. This is what a carbon looks like, carbon NMR. There's not much to it. You just see 3 environments and the chemical shift for where they show up. That is the standard way that carbon NMR is run, and really, just like I said before, it's a lot less information than proton NMR usually gives you, but it can be useful on occasion, but in general, proton NMR is much more information, and usually all the information you need. So I did mention previously that carbon NMRs wouldn't show splitting because there's not usually a carbon-13 next to a carbon-13. But what is next to these carbons is hydrogens. And of course, hydrogens have small magnetic fields, so those hydrogens actually do have effects on those carbons and do split them up. So normally when we run a carbon NMR, we do what's called proton spin decoupling. And essentially we send that radio wave at the hydrogen's frequency and just cause them to rotate around up and down and side to side. Therefore, they're not going to have any effect on the carbons. The reason for that is it's hard to tell the difference between a doublet or two single carbon environments by carbon NMR. So normally what happens is you just run them with the hydrogens having no effect. You can of course turn that off if you want to, and what would happen is carbons that are all by themselves with no hydrogens would appear as singlets. Carbons that have one hydrogen would be doublets. This carbon over here, which has two hydrogens attached to it, would actually show up as a triplet. This carbon on the right that's a CH3 would actually show up as a quartet. So let me show you what this spectrum looks like for this specific sample. You may, if you remember where the peaks were before, you may notice that those peaks are in exactly the same place. We've got this one right here around 30, and notice that that is a quartet in this case. So this signal right here is a quartet, which is what we had predicted right here in that 0 to 35. That means that it's a CH3 because this is a carbon with three hydrogens attached to it. Likewise, this middle one, which was a CH2, shows up as a triplet in this case. Finally, the carbon with no hydrogens next door shows up as a singlet, and that's where we see it right there all by itself. So those three peaks are at the exact same places as that previous carbon NMR I showed, but in this case we're doing what's called off-resonance decoupling. It's basically where it will allow all the carbons to be split by their local hydrogens. It becomes very hard to read if you don't have a really good high-powered NMR, and also if you haven't run it for a sufficiently long period of time. Therefore, it's normally not done. Again, it's at a certain point the information is overkill. We can tell most of what we need to know from hydrogen NMR. The carbon NMR will usually seal the deal if we need it. Doing this off-resonance decoupling to see doublets and triplets and quartets in carbons, it is helpful on occasion, but usually you can figure this information out without it. Let's look at one more molecule before we wrap this up, which is a 4-carbon ketone. So the hydrogen NMR would show three environments. We would have one here, one there, and one there. But the carbon NMR would have 4 environments because there are actually 4 carbons in this molecule, all of which are different. The most notable one would be this C double bond O right here, which would appear between 160 and 210 ppm. And we would expect all of the other ones to all show up. They would be, of course, different. There would be 3 environments for these 3 carbons, but they would all be in the range of roughly 0 to 35 ppm. Furthermore, based on the number of hydrogens, we could tell what the off-resonance decoupled spectrum would look like. A CH3 would be a quartet because it has 3 hydrogens attached. The carbon right here of the carbonyl would just be a singlet because it has no hydrogens. CH2 would show up as a triplet, and the CH3 on this side would also be a quartet, just like the CH3 that is on the left. And here is our spectrum. We have a peak over here on the left, which is right around 210 ppm. It is a singlet in the off-resonance decoupled, which is on the top. Your normal classical carbon NMR is here on the bottom. It just has a normal peak that are not split by their hydrogens. So you'll see that we have one peak right down here, kind of actually around 7 or 8 ppm. That would be this CH3 for this to the right. There's nothing going on with it. When you allow it to be split by its hydrogens, notice that it is a quartet because it's got 3 hydrogens around it. Next we have one right around 30. That shows up, in this case it's the singlet because the lower one is where we have essentially turned off the hydrogens. But you'll see that that is a quartet, so that would be the CH3 off to the left. Very nearby is the CH2 that is right next to the carbonyl. So these two correspond to the two carbons that are right next to the carbonyl. This is the carbon that is 2 carbons away from the carbonyl, and here's the carbon that's in the carbonyl. So if you get used to hydrogen NMR, we would never see this carbon right here because it doesn't have any hydrogens. But just remember, in carbon NMR, whether or not these carbons have hydrogens attached, the fact that they're carbons causes them to show up in NMR. And you can see in this case why integrating would be no good. This one is quite small, these two are quite tall, and really that doesn't mean anything in particular. It turns out that the more buried in the molecule they are, the shorter the peaks appear. So this carbon right here isn't attached to any hydrogen, it's kind of stuck in the middle, and you'll notice it's a little bit of a shorty. So that's kind of a general rule of thumb, but it doesn't really help us out very much. Whether they're short or tall, the integrals are no good, and the splitting with carbons is no good. So really all we have to go by is how many environments there are, and because this is the main one that we do, only the second thing, the only other thing we have to worry about is the chemical shift, or where they're going to show up. Alright, so thank you very much. I will give you no additional homework to worry about for these carbon NMRs. In class we will also talk about two-dimensional NMR, which is very exciting, but I want you to be aware of carbon NMR. Again, the proton NMR is the most important and the most helpful, but carbon NMR is useful in its own way. Thank you very much. Have a good day.